So what is chemistry? Well, its most basic definition is that it's the study of stuff, but let's make that a little more formal. It's the study of matter. We study its nature, its properties, its transformations, and its interactions with other matter and with energy. So what is matter? Matter is anything that has a mass and occupies space. Or we can also state it as anything that has mass and occupies volume. So some examples of matter, well, everything around us, the air that we breathe, the grass, the trees, your skin, your DNA, the food that we eat, your hair, your fingernails, the chairs and the desks in the classroom. This is all matter. Now keep in mind that, again, matter has mass and occupies volume or space. Light and energy are not matter. And we'll talk about light and energy a little bit later. So when we talk about matter, we are usually interested in the properties of matter. And that includes the physical properties and the chemical properties of matter. So what is a property? It's a characteristic used to describe matter. So I might describe a person as being 5'7", 120 pounds, brown hair, blue eyes, and so on. So when we describe matter, we can describe the physical properties and the chemical properties. So the physical properties include size, color, temperature, boiling point, electrical conductivity, melting point, and so on. Chemical properties might include things like flammability, chemical composition, chemical stability. Does it burn in air? Does it not burn in air? And so on. So let me give you an example here. Let's talk about the physical properties and chemical properties of water. So for water, the physical properties would include things like it's a colorless liquid, it's odorless, it has a melting point of 0 degrees Celsius, it has a boiling point of 100 degrees Celsius. And of course I could go on and on describing the physical properties of water. Now, maybe the chemical properties, so water does not burn. Its chemical composition is 11.2% hydrogen and 88.8% oxygen. Let's do another compound. Let's talk about sugar, table sugar, also called sucrose. Some of the physical properties. It's a white crystalline substance. It has no odor. As far as its chemical properties, its composition is 6.4% hydrogen, 42.1% carbon, and 51.5% oxygen. Another chemical property of sugar is that it will burn in air. But we'll talk more about chemical properties later. For now, we're going to focus on physical processes or physical changes. It's more convenient to talk about physical processes. So let's go ahead and define that. A physical process is a process where a substance changes in form but does not change its chemical composition. In other words, it's the same substance. So for example, when I take that ice cube out of the freezer and I place that ice cube in a glass, it is eventually going to melt. It's going to go from solid, which is ice, to liquid, which is the liquid water. Now, the substance, the ice, has changed its form, but it's still made up of water molecules. The chemical composition is the same. See, chemical change involves the production of a new substance. But in a physical process or physical change, the substance does not change its chemical composition. Even if I take that liquid water and boil it, okay, now we're going to have gas molecules, but it's still water molecules. Now, we talk about 3 states of matter: solid state, liquid state, and gas state. There's actually one other state that we don't talk about in introductory chemistry, and that's called a plasma. But we're going to focus on the solid liquid and gas states. Let's take a look here at this molecule of water. We haven't talked about molecules yet. We haven't talked about molecules. We haven't talked about ionic compounds, but we will later. But for now, I want to focus on this water molecule. And this red here is an oxygen atom, and we have 2 hydrogen atoms. So water is composed of an oxygen atom with 2 hydrogen atoms bonded to that oxygen. So for now, what I want to talk about is change of state. We already know what the state of a substance is. Either it's in the solid, liquid, or gas form. But a change of state is a physical process where the substance goes from one state to another. So for example, that ice cube melting, that is a change of state. And again, it's a physical process. Changes of states include freezing, melting, evaporation or vaporization, condensation, deposition, and sublimation. You probably haven't heard of these 2. I will talk about them in a few minutes. Just for your information, a little bit later in the semester, we're going to learn how to name compounds. And of course, H2O is water, and it has this chemical formula, 2 hydrogens and 1 oxygen. The formal name for water is dihydrogen monoxide, but we just call it by its common name, water. Let's take a look at how these molecules, these water molecules, might look in each state. Here we have water in the solid state. Notice how the molecules are very close together. They're in a very ordered arrangement. Okay, that's water in the solid state. So in the solid, any solid, whether it be water or sugar, let's say, any solid is going to have a definite shape and a definite volume. So a solid does not change its volume. It's not dependent on the container that we put it in. Here's water in the liquid state. Now notice the water molecules, they're still associated with each other, but now they can move. Water is fluid. The molecules can slide across one another, and we know that a liquid has a definite volume. So 1 cup of water is 1 cup of water, whether I put it into a tall graduated cylinder or into a bowl. But it has a variable shape. So liquids will take on the shape of their container, although the volume is going to remain the same. And then we look at water in the gas state. Notice how far apart these molecules are. They're not associated with each other at all. So gases have variable shape and variable volume. Think about helium. We fill up balloons with helium. So we have different shaped balloons. And again, the gas is going to vary in its shape. It's going to accommodate the shape of the container and also variable volume. And that's because, again, the gas molecules are not closely associated. Let's take a look at some changes of state. Here I have a gas, solid, and a liquid. And let's start with the solid. Okay, if we go counterclockwise, so a solid can melt to form a liquid, and a liquid can be vaporized or can evaporate into a gas. Our ice cube, our solid ice, can melt. When we go from solid to liquid, this change of state is called melting or fusion. Fusion is the same as melting. When we go from the liquid to the gas state, this is called vaporization or evaporation. And then, look at this one. When we go from a gas directly to solid, this is called deposition. Now let's go clockwise. When a solid goes directly to a gas, this is called sublimation. And I'll get back to sublimation in a moment. When a gas goes from gas phase to the liquid phase, that is called condensation. And then a liquid to a solid, this is called freezing. That's what happens when you put liquid water in the freezer and you end up with ice cubes. Notice that each change of state, so let's take a look at melting. So we have melting, solid to a liquid. Each change of state has an opposite process. So from liquid to solid, that's freezing. Here, from liquid to a gas is vaporization. The opposite is gas to a liquid, which is condensation. And then a solid to a gas is sublimation, and a gas directly to a solid is deposition. So sublimation, you might or might not have heard of it, and this is where a substance passes from the solid state directly into the gas state. So some examples of sublimation: dry ice, that's actually solid carbon dioxide, and dry ice is a solid. It never melts into a liquid. It goes directly into the gas phase. Another example would be those air fresheners, those Airwick air fresheners. What you do is you twist them, open them up, and they have that substance inside. And basically what it does, it sublimes. And it doesn't melt all over your table, okay? It just sublimes. It goes from the solid state directly into the gas state. Mothballs, most of you probably don't remember what mothballs are, but they also work the same way. And then deposition is the reverse of sublimation, and this is where a substance passes from the gas state directly into the solid state. So what causes a change of state? Well, I know we haven't talked about molecules yet, but we'll talk about molecules and other types of compounds later in the course. But let's think about what happens with water molecules. It turns out that atoms and molecules have attractive forces. In other words, there are certain forces of attraction that hold the molecules together. This is why water molecules do not fly out of your glass. There are attractive forces between molecules that keep them as a liquid, or keep them in the liquid phase. We call these attractive forces between molecules intermolecular forces, or you can think of them as attractions. So, substances that have strong intermolecular forces will stay closely associated. What that means is, when there are strong intermolecular forces, that means higher melting and boiling points. So what does this mean? Well, let's take a look here. Water melts at 0 degrees Celsius, and methane, which is natural gas, methane melts at a negative 182.5 degrees Celsius. Now, we know that water at room temperature is a liquid. And room temperature, which is about 22 degrees Celsius, methane is a gas. We use it, right, to cook our food and to heat our homes. So methane is a gas at room temperature. So why is that? Why is one substance a liquid and the other substance a gas at room temperature? Well, water has stronger intermolecular forces than methane. So in other words, water molecules have stronger attractions for each other, where methane molecules have very weak attractions for one another. So it's therefore a gas. Water has very strong intermolecular forces, and one of the reasons why it has a special type of intermolecular force called hydrogen bonding. So here we have some water molecules, okay? And here's what happens. You have a hydrogen, which is bonded to an oxygen, If hydrogen is either bonded to an oxygen, a nitrogen, or a fluorine atom, then it's capable of hydrogen bonding with other like molecules. Now we're going to talk more about this type of bonding much later in the course, but for now I just want to give you an idea of the attractions between molecules. Basically what will happen is if hydrogen is bonded to an oxygen, a nitrogen, or a fluorine, it can hydrogen bond with another molecule that contains oxygen, nitrogen, or fluorine. So these attractions between these water molecules are very strong. So let's take a look here. So here we have water that's in the solid state, and when water molecules are in the solid state, again, you have a very ordered crystal there, okay, and the molecules are very, very close to one another. Now, it's going to take some energy in order to convert the water from the solid state to the liquid state. In the liquid state, you still have strong attractions between molecules of water, but they're able to move more. Now, they have more freedom. Okay, water is fluid. So it takes some energy in order to overcome the intermolecular attractions. Well, when you take an ice cube out of the freezer, and let's say it's at room temperature, that ice cube is going to eventually melt. So that ice cube is absorbing heat or energy from the surroundings to become liquid water. Now, if I were to take that same ice cube and place it outside on a cold winter's day where the temperature is below 0 degrees Celsius, well, that's going to be a different story. That ice cube is not going to melt, and that's because there's not enough heat energy for that ice cube to absorb on that cold winter's day. And then finally, I can take this liquid water, put it in a pan, put it on the stove, turn the heat up, and we end up with water in the vapor state. So again, by adding that heat, the water molecules are going to become more energetic, and it's easier then to overcome the attractions between the molecules of water. Water molecules become gas molecules. So when they're in the gas state, these molecules have absolutely no attraction whatsoever for one another. And we'll talk more about gases later in the semester. It turns out that the state of a substance, whether it's a liquid, solid, or gas, is going to be dependent on temperature. So let's go ahead and define temperature. Temperature is an indication of heat transfer. It gives us a numerical value. Heat is defined as the flow of kinetic energy from a warm to a colder body. So let's define kinetic energy. Kinetic energy is the energy of motion. Let's say I have a rubber band. Let's say I stretch it as far as I can without breaking it. When I let that rubber band go, we're increasing the kinetic energy, the energy of motion. So again, heat is the flow of kinetic energy from a warm body to a colder body. So heat always flows from hot to cold. So for example, during the day, when the sun is out, your home will absorb heat from the sun. Now at night, what will happen? The sun goes down. It's much cooler outside than it is in the house. So the heat will then flow from the house to the outside surroundings. Again, heat always flows from a warmer body to a colder body. I have the figure of water in the solid, liquid, and gas state. We call heat thermal energy. Heat is energy. Heat is also called thermal energy. And thermal energy is actually kinetic energy. Let's think about the ice melting. So we take the ice out of the freezer, put it onto a table, and let's say we're at room temperature. what happens is, as the thermal energy flows into the ice cube, the energy from the surroundings flows into the ice cube, the kinetic energy starts to build within the ice. So then the individual water molecules can start to break away from this very ordered, tight structure into the liquid form. The ice then starts to melt. Now, when I put this water on a burner on the stove, we're providing more energy. Now, kinetic energy starts to build within the water, and then the attractive forces between the water molecules are overcome because, again, we've increased the kinetic energy. There's more movement. The molecules have more energy. Now they're able to completely break away from one another and to become gases. I think then we can conclude that when going from the solid state to the liquid state, we have an increase in kinetic energy. When going from the liquid state to the gas state, again, an increase in kinetic energy. When kinetic energy increases, we call this an endothermic process. An endothermic process is the absorption of energy. So when that ice cube melts, it has to absorb heat from the surroundings. That is an endothermic process. So melting, vaporization, and evaporation are endothermic processes. In an endothermic process, you can think of the substance going from a lower energy state to a higher energy state. What about the case where a liquid goes to solid? So what about freezing? Well, in that case, we have an exothermic process. When liquid water, for example, is converted to ice, when we put that liquid water into the freezer, actually energy is released in the form of heat. And that is an exothermic process. You can think of an exothermic process as being a process where the substance goes from a higher energy state to a lower energy state. Think about it. Think about water going from the liquid state to the solid state. What's happening here? Well, as it freezes, the water molecules are becoming more closely associated with one another. That means that this solid is becoming more ordered. The molecules, again, are becoming more closely associated. But when that happens, there's a release of heat, and that is exothermic. The same when a substance goes from the gas state to the liquid state. Condensation, that is an exothermic process. Again, the substance is going from a higher energy state to a lower energy state. So exothermic and endothermic are two very important concepts that we'll revisit as we go. We can conclude that the physical state of a substance is dependent on the kinetic energy and intermolecular forces within the system. So let's take a look. In the solid state, there's minimal kinetic energy. That means very, very strong intermolecular forces, right? Because in the solid state, these molecules are very highly ordered. In the liquid state, still strong kinetic energy, strong intermolecular forces. It's less ordered. The molecules are less ordered, and they have more freedom to move about. And then finally, in the gas state, we have very strong kinetic energy. Huge. Because these gas molecules now have no attraction for one another. There's no attractions between gas molecules. So very weak intermolecular forces. Very random, very chaotic, very high kinetic energy. This concludes this section on physical processes. At this point, I would expect you to be able to talk about the changes of state in terms of being endothermic or exothermic. One question I would have for you, sublimation, would that be an exothermic process or an endothermic process? Well, sublimation is where we go from the solid state directly into a gas state. You're going from a low energy state to a high energy state. So that would be an endothermic process. The reverse of sublimation, deposition, going from gas directly to a solid, would be an exothermic process. The endothermic processes are melting or fusion and vaporization, evaporation, sublimation, the exothermic processes, condensation, deposition, freezing. So for class tomorrow, make sure that you understand the concepts from this video, and we'll be ready to work on some problems and get into a more in-depth discussion.